This is the standard form of a polynomial function of nth degree. I have a theory we're going to share today about the left and right-hand behaviors of the polynomial. Now, it's very important that you understand how we say left and right in mathematics, which goes back to our last lesson. So, here is the theory that as x goes to the left, f of x is heading in the same direction as a naught x to the n. Also, as x goes to the right, f of x is heading in the same direction as a naught x to the n. So if I'm looking at my basic polynomial function, and I look at that lead power function, that is how the graph of the polynomial is going to act on its left and right hand side. Let me give you an example. For instance, let's take a look at the graph, or this function here. According to my theorem, if I asked you to answer what was happening to f of x as x went to the left and as x went to the right, basically my theorem says all I need to know is what's happening with the lead power function. Now, if we take a look at this, this is an even power function. It has a negative lead coefficient, which means that this power function is going to graph something like that. It's even with a negative lead. So, my polynomial does not look like that. That's not what my theorem says. My theorem says at the end, at the left and the right of my polynomial is doing what the lead power function is doing. So, if I want to know what f of x is doing then, as I go to the left, it's doing the same thing to the left as this is doing to the left. The function is going down. As I go to the right, f of x is doing the same as this power function is. It is going down. So my lead power function is going down to the left and right, which means my power function will be going down from the left and from the right. An important thing to realize is that even if we graph it in the calculator, a lot of times the calculator could give us the wrong answer because it doesn't really know how to answer the question. Let me explain. I'm going to push y equals, I'm going to clear out anything else I have in there, and I'm going to put this function in there. And I'm going to look at it in a regular window, which is zoom standard. That takes me from -10 to +10 for x and y. Oops. Let me turn on my grid. Hang on a second. My mode. Format, I mean. I'm going to turn my axis on. Had them off earlier. Now, what you may or may not notice is at the very edge to the left and right, you see a little something, but you may or may not notice it. But when you look at the graph, it appears in the middle that it's opening up. The problem is the graph did not understand your question. It just graphed what you told it to graph. And sometimes it's really, really, really difficult to know how to graph it unless you already know what the left and right hand behaviors are. Then you don't know what you're looking for. So, if I was to change my window, instead of from -10 to +10, I went from -20 to +20, and I did a zoom fit, which means the calculator is going to try to set the y values for me, but I still had to tell it the x values. Notice, I get almost a completely different looking graph because I'm so zoomed out that I cannot even see on this graph that I was going up for quite a bit. But eventually, as you'll notice, the left and right hand behavior of the graph is going down. It must be going down. Very important lesson we just learned here. This calculator is not a useful tool at all to answer any of the questions on the final exam. Not for this type of question. I will make questions, they will make questions on the final exam that are specifically designed that you understand this theory and you can't just look it up on the calculator. For instance, you can play around quite a bit on a graph that looks like this. First thing you need to identify is the lead power function, and this one is not in descending order. So to identify my lead power function, it's the one with the largest exponent, which means the left and right hand behavior of this polynomial eventually will look like this. And since this is an odd power function, I know the left and right hand behaviors go in an opposite direction. And like a straight line, if my lead is negative, I'm going in this direction. From left to right, I'm going down. Of course, you also have bend on it, so the power function really looks something like that. Now, this allows me to answer the question as x goes to the left. This is my left-hand side. Y is going up. As x goes to the right, this is my right-hand side. Y is going down. Okay, now that we have talked about what's going to happen on the left-hand and right-hand side of the polynomial, we're going to talk about what is possible to happen in the middle of a polynomial function. Now, a polynomial function has a maximum of n minus 1 terms. I'm going to explain what a turn is. A turn is any time in a graph that you're going from increasing to decreasing, or from decreasing to increasing. So this graph has 2 turns. However, it's very important to note that if I was to push these together, the graph could end up looking like this. This graph technically has 0 turns because the graph is always increasing. But what you should notice about this graph is that it really looks like I had 2 turns smashed into one. This is sometimes referred to as a step. And anytime I see a step on a graph, mathematically, that's equivalent to having 2 turns. It's not 2 turns, but it takes the same mechanics, same mathematics to produce 1 step as it does to produce 2 turns. So, let's take a look at something. I'm going to tell you everything I know about this polynomial function at this point. I know that since my lead power function is a 4th degree power function, that the graph of that power function opens both up or down, and I know that because it's negative that both sides open down. So now I know that the graph of my function on the left of f of x is going to be going down, and on the right of f of x it's also going to be going down, just like the power function, negative 3x to the 4th. However, f of x is not a power function, it's a polynomial function. It could have up to a total of 3 turns, and that's a maximum amount. You don't ever necessarily know how many turns, all you know is how many are possible. So I'm going to just make a possible graph of what I'm looking at here. It may possibly look like something like this. 1, 2, 3 turns with the left-hand side going down and the right-hand side going down. So these are just the possibilities. I know for a fact the left and right-hand side go down. That I know for a fact. I just don't know for a fact whether this has less than 3 turns or exactly 3 turns. Okay, I'm going to take a look at another function. I have f of x equals 1/2 x to the 5th minus 10x to the 4th plus 22. This is a polynomial function. All my exponents are integers. I know that it is a 5th degree polynomial because that is the power function with the largest exponent. Now, I know that the left and right hand behavior of this graph is going to look like this graph. Now, it is an odd, which means its left and right hand behavior is going to behave as all odds do, like a line is also odd. And I have a positive lead, just like a line with a positive lead, with bend from left to right, it's going up. Which means the left-hand side is going down and the right-hand side is going up. So now I'm going to make a possible graph of my function. I know on the left it's going down, and on the right it's going up. But this is not a power function, it's a polynomial. I got multiple turns possible. So this object has a possibility of having up to 4 turns. 1, 2, 3, 4 maximum. I can tell you the left and right behavior. As x goes to the left, y goes down. As x goes right, y goes up. These are all the things I can tell you about this just by looking at the formula. I know the left and right hand behavior and the maximum number of turns. If you were given a graph of a polynomial with m turns, it must be at least an m plus 1 degree polynomial function. An example of this. Given that the graph is a polynomial function, and this graph has 2 terms, then this graph is at least a third degree polynomial function. Also, since it's a third degree polynomial function and my end behavior is increasing from left to right, I could also determine that my lead coefficient must be a positive number. Okay, I'm giving you a polynomial function. Now, technically speaking, the graph of this polynomial has only 1 term. However, it also has a step. A step is always equivalent of 2 terms. Based on this information, I could determine that this polynomial must be at least 4th degree polynomial. And because both sides open up, like the power function ax squared, I know my lead coefficient must be positive.
But it must also be even, right?
Also, not the coefficient does not have to be even, but the degree must be even. We know that it has to be even if both sides open up in the same direction. If both sides open up in opposite directions, it must be odd. So if we go back to the last one, not only did we know it had to be a 3rd degree, but it also must be an odd poly. So meaning it could be a 3rd degree poly, but it also could be a 5th degree. And it's possible that it's a 7th degree polynomial. Because all we know is it must be at least 3rd, and it must also be odd. We're now going to attempt modeling data with a polynomial function. First thing I'd like to do is get a visual of this data before I decide what I want to model it with. So, starting with our graphing calculator, we're going to enter the data. Let me put that over here so you can see it better. Stat, edit, going to clear my L1, clear my L2, -3 through, oops, yep, we're good. Put in my x values, I'm going to put in my y values. Once I have my x and y values in the calculator, I'm going to push y equals, clear any equations I have so they don't have to look at them. Go in and turn my plot on, push my zoom button, and go down to zoom stat. Okay. From this, I am going down from left to right. It does not appear that I have any curves. Correct? Since there are no curves, 0 curves, this would leave me a 1st degree polynomial function. What is a 1st degree polynomial function? Let's take a look at a 1st degree polynomial. a naught to the x plus. That's also known as a straight line. The equation of a line is a polynomial function. This has no terms. I can also tell you from looking at it that my lead coefficient more than likely, well, is going to be negative. So, stat, calculate a linear regression. Also, if you, let me push this up here for a second so you can see what I'm about to do right now. Find your variables button. Variables. Clear. Stat. Calculate. Linear regression. Push your variables button right there. Go to y variables. Function is number 1. Push number 1. And going to push number 1 again. This is going to do two things for me. When I hit enter, not only is it going to give me the equation, but if I push y equals, it plugged it in there for me as well. So not only did it do the statistical regression for us, it plugged in the equation of the line for us in y equals. So now all we have to do is push graph, and we have done a polynomial regression. Now, let's look at some of the other options under polynomial regression. If you push your stat button and go to calculate, a quadratic regression is also known as a second degree polynomial function. Going on down the list, a cubic regression would be a third degree polynomial function. Quart regression would be a fourth degree polynomial function. And I believe that is all of them. So your calculator is only capable of first, second, third, and fourth. However, if we were working in Excel, you would realize, I believe with Excel you could go through a ninth degree polynomial regression. So our calculator is a little bit slacking on this particular skill. So, okay, we're going to attempt to do another polynomial regression. With this one, I'm going to go ahead and enter my data, stat, edit. Notice my x values are still from -3 to +3, so I don't have to change them. But I am going to go and clear my y values and re-enter the new ones. Now, since I have new y values, when I push the y equals button, I want to make sure I turn off any equations by pushing clear so I don't get confused at what I'm looking at. All I want to have is plot 1 highlighted. Now I'm going to go and push zoom and go down to zoom stat, enter. This one clearly looks nonlinear. Best estimate, if it is a polynomial function, that it is at least a third degree, because it appears that we have one term and then another term. So from looking at this, I'm going to estimate that this is a minimum third degree polynomial function. That's important that I can identify that visually. So now I can push stat, calculate, Number 6 is my cubic regression, which is a third degree polynomial function. I'm going to hit enter. I'm not done. I'm going to push variables button. Go over to y variable, function, enter, y1, enter. And not only is it going to perform my third degree polynomial regression for me, it's also going to put it in there for me, so when I hit graph, I can see if it matches the data. Looks like it's a very good match. There's my formula, y equals x cubed plus 0. That's very important. If I was writing it by hand, I would not write that 0 there. And I would not write plus minus, by the way, if I was writing it by hand. So, how would I write this out by hand? I would write it out this way. F of x equals x cubed minus 4x. That's it, because b and c are 0.